Hello and welcome to this lecture. In the previous lecture, we saw second order linear ODE with constant coefficients. We saw the homogeneous case and how to solve that. We saw that, and then we saw the forced system case where you have a function q of x which is non-zero, and then you have to guess particular solutions and how the overall solution is the simple addition of the particular solution and the homogeneous solution. Okay, so that is something that we have seen before. So now what we are going to do is to take one complete example of a practical circuit, this RLC series circuit that you will see quite often, and put a DC source on it, and then everything is discharged, there is nothing going on, and then you turn the switch on at t equal to 0, and we wrote an equation for the current I of t in this case. It had a certain form. Now what I have done here is I have divided by L throughout, and then assigned some variables to these r by L and 1 by LC, so that you get a I double prime of t plus 2 alpha I prime of t plus omega naught square I of t equals 0. So this is a standard form. This alpha is called an attenuation factor because the resistance here tends to attenuate the current over time, and then omega naught square is called the natural frequency of this LC circuit. Anytime you have an L and C, 1 by root LC is omega naught, and that is called the natural frequency. You will see why that notion of frequency and all that is actually valid as we see what happens in the circuit when you turn the switch on. Okay, so what's going to happen initially is when you turn the switch on, there's lots of circuit current and circuit loss here. For instance, the current through an inductor cannot rise suddenly, okay, because the current needs to be continuous and differentiable, in fact, right. So L di by dt, or L I prime, is the voltage across the capacitance. So I cannot go up suddenly, and likewise the voltage across the capacitor cannot shoot up suddenly, because the current through the capacitor is C V prime Vc prime of t. So those rules are there. So what will happen when you turn on the switch is there will be no current, I of 0 will be 0 and the entire voltage here will fall across the capacitor for the inductor, I am sorry. So because nothing else can have a non-zero voltage. If this has a non-zero voltage, then the current will be non-zero, that is not allowed. And if this has a non-zero voltage, that is not allowed, because this voltage cannot step up in a capacitor. This can have a non-zero voltage step up, and that will control the slope of the current. So slope of current at 0 is going to be the entire voltage showing up across the inductor, and that you divide by L. So that gives you the slope of the thing. So these are the initial conditions. So the moral of the story is, in a circuit, the initial conditions have to be figured out using circuit laws, and there are some basic circuit laws on what happened in the capacitor, what happens in inductor, what happens in a resistor, and you can use that to figure that out. But the equation itself, we saw how to do this earlier, and these factors alpha and omega naught square are new. I hope this makes it succinct and clean in the notation, and you'll see it will work out okay. So how do I solve this? This is a homogeneous equation. That's nice that we have a homogeneous equation. We don't have to do a particular solution, just the homogeneous solution is enough. So what is our guess for the homogeneous solution? E power st, isn't it? I of t is e power st, and we get this quadratic equation, s square plus 2 alpha s plus omega naught square is 0, and we want to guess we want to find the values for s. Okay, the solutions of this quadratic equation are minus alpha plus or minus square root of alpha square minus omega naught square. A nice form for the solution, and this is why all these definitions and shorthand notation are very, very useful. So there are two solutions here, and depending on whether or not you have two real roots, one real root repeated, or complex conjugate roots, the nature of the homogeneous solution is going to change. We know that also, right? So there are three cases here. These are called three different situations. First is, if you have two real roots, this alpha needs to be strictly greater than omega naught, right? The attenuation has to be high, so you get two real roots, and that is called the overdamped case. Then you have the critically damped case, critically damped case, I should say that correctly, critically damped case, when you have repeated real roots, that is when alpha equals omega naught, okay. And then finally you have the underdamped case, when alpha goes less than omega naught and you have complex conjugate roots. Okay, so these three terms are worth remembering, because the second order systems, this is a second order system, right? Second order systems are very, very common all across engineering, science and all that. Commonly you get these many things that satisfy second order property. For instance, you may have seen these doors that have door closers on them, right? So you push the door a little bit, that's the initial DC voltage that you are giving, and then when you release it, what happens to the door, the position of the door is controlled by a second order equation. So, even in that second order equation, it may not be R, L and C, it may be some spring constant, something else, but there also you will have any second order system like this, you will have a natural frequency, you will have attenuation factor, and you will have overdamped case, critical case, underdamped case. Okay, so these are called second order systems. You will study more of this as you go later on, but as a differential equation, these things, you will see how these things control the property of I of t. The solution I of t is controlled by these three things. Okay, so let us see that in the next slide. Okay, so first thing we will consider the solutions. It's nice to define a WD, omega d, which is like the damped frequency, which is square root of, I put absolute value omega naught square minus alpha square here. This is just to take care of the underdamped case and the overdamped case. For both of it works out as omega d. Okay, so why is that? Because you know this alpha square minus omega naught square is showing up inside the square root. It's good to have a shorthand notation for that. So I'm going to call that omega d. That's called the damped frequency. Omega naught is the undamped natural frequency. Omega d is the damped frequency of the circuit. If it's overdamped, alpha is greater than omega naught. We saw that there are two real roots, and the two real roots are minus alpha plus omega d, minus alpha minus omega d, right? Minus alpha plus omega d and minus alpha minus omega d. So, and the solution is going to be I of t is a e power the first root. So, you can see I have taken e power minus alpha t common outside. So, I get this, but you can see what I have inside is e power minus alpha plus omega d, that is the first term here, right? These two things together is minus alpha plus omega d, and the second term is e power minus alpha t minus omega d. Normally, you should have two constants. The reason I put one constant is I know I of 0 is 0, right? So, I need to have I of 0 equal to 0, and that will make sure that both the constants are the same. The constant multiplying the first solution and the constant multiplying the second solution have to be minus of each other to get I of 0 to be equal to 0. Maybe I can show you that real quick. So, the general solution is going to be a times e power minus alpha plus omega d into t plus b times, or maybe I will call it a times a1 a2 maybe, right, e power minus alpha minus omega d into t. This is what we have seen, but then I of 0 is actually a1 plus a2. It has to be equal to 0. That implies a2 is minus a1. Okay, and then I of t becomes a1 can be pulled out common, e power minus alpha t can be pulled out common, and you get omega dt minus e power minus omega dt. Okay, so it's a quick derivation. I've not used a1 here. I've used just a1 equal to a to get a nice thing. So this is the I of t in the overdamped case. Okay, so you see this this is going to go off to 0 if alpha is positive, right? So eventually it will go off to 0. This one that's going to happen, right? You can see so alpha is greater than omega naught, so that makes this go to 0. Okay, so next you have the critically damped case when alpha equal to omega naught. In that case, what would happen is, okay, so in that case what would happen? This is overdamped. So if you look at critically damped, you know I of t is going to be b1 e power minus alpha t plus b2 e power, b2 t e power minus alpha t, right. So this is what this needs to be. So you know I of 0 equal to 0 is what? I of 0 is b1, and that needs to be equal to 0, right. I of 0 is b1, no, t equal to 0, you will only get b1, b1 is 0. So this ends up being just b2 t e power minus alpha t. Okay. So I have not called b2 here, I have just made it b. So critically damped, alpha equal to omega naught, the damped frequency just becomes 0, it goes away. So you get bt e power minus alpha t. Okay. The interesting case is also, equally interesting case is underdamped case when alpha goes less than omega naught, in which case you have two complex conjugate roots, and in the complex conjugate roots also you have to get, you are supposed to get underdamped complex conjugates. I of t will be c1 e power minus alpha t sin omega dt plus c2 e power minus alpha t cos omega dt. Now, if you put I of 0, you are going to get c2, right. This first thing will go away because the sign is 0 and this is 1, so you get c2 and that needs to be 0. So this just becomes c2 e power minus r, C1, I'm sorry, C2 is 0, C1 sine omega dt. Okay. So, you notice here I want to point out 3 different types of solutions. Overdamped case is exponential fall, purely exponential fall. Okay, this difference of 2 exponentials, but sort of exponential fall. Critically damped case is t times e power minus alpha t. Okay, it's nice. Omega d just disappears. Okay, it just goes as e power minus alpha t by t times that. Finally, the underdamped case has sinusoidal oscillations multiplying e power minus alpha t. Okay. So, how do you find ABC? You find ABC so that I prime of 0 is VDC by L. Okay. So, that also you know. So, you differentiate this at and substitute t equal to 0, you will get some expression for A, B and C. Okay. So, this is how you do RLC series circuit solution. So, you have the damp frequency showing up, the attenuation factor showing up and some constant showing up in front. Let us see a plot. This is a slightly famous plot for second order systems with DC input. So, you see here there are 3 cases. So, I've put zeta, this Greek letter is called zeta. Zeta is alpha by omega naught. Okay. So, you see here if zeta is greater than 1, it is overdamped, zeta equal to 1 is critically damped and zeta less than 1 is underdamped. So, what I plotted here is I of t for different ranges of zeta. Let us begin with zeta going less than 1, 0.4, and you see that causes oscillations. No? So, you see the sine wave, but the sine wave is multiplied by e power minus alpha t. Okay. So, there is one e power minus alpha t which will multiply this. So, the sine wave will attenuate. It will initially start very high, and then as this alpha factor comes in, e power minus alpha t is going off to 0. No? Eventually, it will go off to 0, but then it will oscillate and go off to 0 like that because of the sine thing here. This go negative, it will oscillate, very small, but it will keep on oscillating, it will never die down. As you increase zeta 0.6, 0.8, the oscillations are rapidly coming down, and then when zeta becomes 1, right, exactly 1, that is the black curve, there is no oscillation anymore, it is t e power minus alpha t. Okay. So, if you do not want oscillations and you want the fastest possible fall, you have to do critically damped. Okay, zeta has to be equal to 1. Now, when zeta goes above 1, notice what happens. It is not oscillating, but what happens is it does not die down to 0 as fast as you did when you did not have, because the WD will come in, the omega d will come in, and that omega d makes the fall go slower than what it should be, because it subtracts from alpha. No, see, minus alpha plus omega d. So, it's just it subtracts, I'm sorry, minus alpha plus omega d. So, it reduces the way the exponent's constant, so it will fall down slower. Okay. So, that happens here. So, notice here how you need to be comfortable with e power minus constant into t. What happens when the constant changes to the plot, right? So, in this multiplication by these guys, you can see that this is how the behavior goes. Okay. So, we have the overdamped case where it does not go too high, but then it only comes back to 0 very, very slowly. But I hope you see that I infinity is 0 for all 3. So, a second order system with DC input, with just an initial input and then you let go, do not give anything else, then it will eventually die down to 0. How quickly it dies down to 0, this depends on these parameters. If it is underdamped, it is going to go both sides. So, for instance, from the door analogy I gave you, if you are underdamped, then the door will go close, it will go past it to the other side and then come back and then it will settle down. You might have seen some doors like that, no? When you pull it out, it will go this way, that way, stop. You might have also seen overdamped doors. The door compensation will be so damped so that you open it, let it go, it will take a long time to slowly come back. Okay. But well designed door stoppers will be critically damped. If you critically damp them, it will come back smoothly and then halt there, and it will come fast also. It will come at a good speed and it will come and stop there. Okay. So, this is also true in circuits. If you have an RLC system, this is going to show up for the homogeneous solution when you have a DC input. Okay. So, that is first example I wanted to give you. The next example, I will do it real quick. I won't go through them in great detail, but let me I'll just show you how this works. Okay. Now, I have an RLC circuit with an AC source, okay, A sine omega t. Now, the equation is sort of the same, except on the right hand side you do not have 0, you have the derivative of this guy, okay. AW cos omega t, but the division by L comes because I am dividing by L here throughout, right. So, I divided by L here throughout, so I get AW by L cos omega t. I have the same 2 alpha and omega naught square showing up. And the initial conditions now will change because sin omega t is 0. Everything is 0 at time 0, so nothing will be there at 0. So I of 0 will be 0, I prime of 0 will be 0. Okay. But what do I know about the form for I of t? This is important for any circuit which has this right hand side non-zero, right? If your right hand side is non-zero here, then what happens is there is some, okay, this is all omega. I think some places I put w by mistake. I think it's all omega, omega. Hope it's clear to you. Okay. So the general solution I of t is going to be sum of a transient solution plus a steady state solution. The steady state solution is the particular solution that we spoke about. The transient solution is the solution for the homogeneous equation. Okay. So and the initial conditions are there. Okay, homogeneous solution was done previously. Just now we saw there were 3 different cases. It could be critically damped, overdamped, underdamped. In all cases, the transient solution will go off to 0 eventually. Okay, when t goes to infinity, it goes to 0. How it goes to 0 changes, but it eventually goes off to 0. Okay. Now, particular solution, I have to guess some linear combination of sin omega t, cos omega t. Okay, so that's what I'm going to guess. And if I do that, if I plug it into this equation and equate the coefficient of sin and cos, I will get these 2 equations. Okay, omega naught square minus omega square p. Maybe I should show this. This is not too difficult to show. Okay, so I've got this equation here, which is I double prime of t plus 2 alpha I prime of t plus omega naught square I of t is equal to AW by L cos omega t, right. I am putting I of t equals p times sin omega t plus q times cos omega t. I hope it's p and q for sin and cos. Okay. So, if I plug it in here, I am going to get omega naught squared times p sin omega t plus q cos omega t plus I am going to get here 2 alpha times p omega p cos omega t minus omega q sin omega t, right. And then I have my I double prime, which is going to be the derivative of this, or you can even differentiate this twice. You will get omega squared minus omega squared sin omega t minus omega squared cos omega t. Okay, so this is the thing, and this needs to be equal to AW by L cos omega t for all t. So what you can do is you can find the coefficient of sin omega t on the left side, cos omega t on the left side, equated to the coefficients on the right side. Let's pull out sin omega t. If you pull out sin omega t, you're getting you're going to get oh, I forgot a p here, sorry. Okay, minus omega squared p minus omega squared q. Okay, so if you pull out the sin omega t here, I'm going to get p times omega naught squared minus omega squared. Okay, so this is the sin omega t, this is sin omega t, there's one more sin omega t here, and that would be minus 2 alpha omega q, this whole thing multiplying sin omega t. Okay, then I have cos, and cos also is going to be plus omega naught squared minus omega squared q cos, okay, not cos, I'll write it finally, and then plus 2 alpha omega p cos omega t equals a omega by L cos omega t. So this guy has to be equal to 0 and this guy has to be equal to a omega by L. Okay, so that's the equation that I have written here. Okay, those are the equations I have written here. Okay, so you see here, this equal to 0 means p times this guy is equal to 2 alpha omega q, and this is this. Okay, so you can substitute it back here, and then you have to identify one more thing here, right? You remember we did this in the RC solution also. Something times sin plus something times cos, you can sort of write it as sin omega t plus phi, right? And q by p will be tan phi, and you can write it like that. Okay, so I can do all that. I'm not showing that detailed simplification. So it turns out finally when you write everything together, you will get I infinity of t to be a by mod z sine omega t minus phi. This is a very, very common way in which people write steady state voltages and currents in a AC circuit. This is called using the idea of phasors. That's something that they do in circuit, but this just comes from the solution to the differential equation. And we did this even in the RC circuit case, right? You might remember that. So in this case, this Z is going to be R plus I omega L plus 1 by I omega C. Once again, a complex representation, and tan phi is basically the angle of this complex number in the r theta plane, right? Omega squared minus omega naught squared by 2 alpha omega, and then you will see that the infinity of t is a by mod c sine omega t minus phi. Okay, so this is the infinity steady state current, and it doesn't die down when t goes to infinity. Even if t goes to infinity, it keeps oscillating. So you have an AC source, it will finally go to this, but it will go through some transient that depends on the damping of the circuit. Okay, so that is the RLC series circuit. Okay, I have not shown a picture here. I'll urge you to plot this in Desmos and see it for yourself. Okay. Okay, so this is a very famous picture. It's called an oscillator. Why is this an oscillator? You'll see that any so it has a very interesting property. The current finally will have a very interesting result. I mean, something that you can't imagine. See, here is a capacitor and an inductor. Okay. I'm going to say the different voltages. Voltage across capacitor Vc of t, I of t is the current, and VL of t is the voltage across the inductor, and t is equal to 0. So I'm going to turn the switch on at 0. Now here are the initial conditions. This is important to understand. The capacitor has an initial charge of 5 volts, something like that. Okay, so it has an initial charge, and the voltage across the capacitor initially, when it's an open circuit, it's 5 volts. Okay, the current when you do that and you turn on the switch. Like these are all 0 plus, okay, 0 plus, you turn on the switch, the current will still be 0 because this inductor current cannot do a step, okay, so it is still 0, but the derivative of the current is going to be 5 by L because this entire 5 volt has to appear here, okay, the 5 volt has to appear here entirely so that the voltage loop is satisfied when you close it, and that voltage is 5, so inductance is L, so the current derivative at 0 is 5 by L. So that is the initial conditions, and there are a few circuit laws. I am not going to go into detail here. VL of t is Li prime of t minus I of t. The current has to be in this direction, for the capacitor. Minus I of t is C Vc prime of t, and VL of t equals Vc of t. Right? VL of t minus Vc of t is 0. You manipulate with this. Basically, you differentiate this and use these guys here. You will get this fantastic looking equation which says I double prime of t plus omega naught square I of t equals 0. And what is this omega naught square? It's again the natural frequency of the LC, which is 1 by root LC. Okay, so this is a famous equation. It's called the wave equation. A double derivative plus a positive constant times the function equal to 0. Okay, it's famous because this shows up everywhere. Anywhere you have a wave, anything you call a wave, this equation will be there behind it. Okay, any wave, sound wave, this wave, and that wave. So, and waves are very common, right? Any oscillatory behavior, pendulum swinging along, anything you have to have an underlying equation, something like this. Okay, why is that? Where does the wave come from? Here is the equation. Let's try and solve it. This is a homogeneous equation, so we are going to get the characteristic equation. We are going to get guess e power st, and that ends up becoming s square plus omega naught square equal to 0. There is no s term. That is a crucial factor here in this second order system. So you have no s term. S square plus omega naught square is 0, and this is also positive. So you end up getting complex conjugate roots on the unit circle I omega naught on the on the imaginary axis, not on the unit circle. The complex conjugate roots on the imaginary axis I omega naught and minus I omega naught. And guess what happens if you do a solution here? This is complex conjugate, so sin omega naught t cos omega naught t is going to be the solution, right? There's no alpha, right? This the e power minus, there's no real part, right? So there's no e power, real part is just gone, it's 0, right? So you only get a sine wave and a cos wave. So I of t is going to be sinusoidal, okay? In particular, if you use the initial conditions, you get I of t to be 5 by omega naught L sine omega naught t. Okay, so here is the magic of this LC circuit. You charged up the capacitor, kept it in open circuit and connected one inductor across it, and then closed the circuit, you get sine wave. Okay, so that's why it's called an oscillator. This is where the waves come from. This is the mathematical equation that governs the generations of sine waves. Okay, So the LC oscillator is a wonderful device. It converts an initial capacitor charge into a pure sine wave. Okay. So with that, hopefully this brought everything together for you. Integration, differentiation, complex numbers, algebraic equations, modeling, and finally you built a very useful device which you can use in practice. Okay. So that concludes this part of the lecture, and this is also the conclusion of the course. So in conclusion, I want to make a few comments about what you've gone through in this course. I hope at the end of this course you have enjoyed an introduction to the utility of mathematics and also the beauty of it, and how some non-obvious problems can be solved using mathematics, and it has a very strong connection to actual practice in science and engineering, and it has a beauty of its own as well, and many of the wonderful results we use have both beauty and utility at the heart of them. And I hope you also picked up an appreciation for the basic method for mathematical problem solving. The specific formulae you learned, the specific ideas you learned are important, are very important for you. These are the important tools that you will need for the rest of your program in the basic circuit analysis, study of signals. For all of them, you will need these tools. Every course you do in this program will use these tools. Okay. However, since this is a math course, I also want you to think about the basic method of mathematical problem solving, which hopefully I have introduced to you through this course. Any problem you want to look at, you want to study it mathematically, you have to first identify the quantities of interest, assign variables to them. Okay. And then you have to explore relationships between these variables, these relationships of various types. These could be algebraic equations, could be differential equations, analytical results, algebraic results, all of these mathematical ideas, concepts you have to use to formulate these relationships, understand these relationships. Okay. Usually what people do is they start with simple relationships. Okay. Most of the obvious easy relationships are easy to come up with, and the heart of mathematics is to deduce more complicated relationships, more profound relationships by logic and clever manipulation of the basic simple relationships. Build on them, build on them, build on them, and you get finally a profound deep result. And hope you've seen enough profound deep results in this class to appreciate why this method is really powerful. So this method of approaching problems and solving them is in some sense universal. It has applications in science, engineering, so economics, so many areas, because any problem solved like this has a very strong mathematical basis, and it's very useful. Okay. So best wishes for the rest of the program, and I hope to see you again in the second version of this Math for Electronics course, where we'll see other ideas in the same spirit. Okay. Thank you very much.